Hello everyone, welcome to our differential equation class. In this video we continue our study of Sturm-Liouville problems. We are going to start with a review of what we have seen about these problems. Then we are going to focus on the property of orthogonal expansions that these solutions of Sturm-Liouville problem has. And then we are going to comment on the relation between these orthogonal expansions and more general expansions which are called Fourier series expansions. So that's the plan for today. Let's start with a brief review of what we have seen about Sturm-Liouville problems. Regular Sturm-Liouville problem, here we are using a weight function equal 1 in all our videos, is to find a number lambda and a non-zero function y of x, solutions of this differential equation subject to these boundary conditions. So the differential equation is a second order linear differential equation for the function y. Here is the number lambda, the eigenvalue that we are trying to find. X belongs to an interval AB, and on the side of the interval we have boundary conditions of this form. From all the solutions of this differential equation, we are looking for the solution that satisfies these two equations at the boundary. One side of the boundary and the other side of the boundary. Here the function p is a function that is positive on the interval. Actually, I think it's on the interval AB. That's why the problem is a regular problem. Okay, what do we have solved? This is a very general problem, so what we have solved is a particular case. The particular case that we are interested in is the case that is going to show up later when we solve the heat equation, and is the particular case where this operator is the simplest possible. Q is equal 0 and P is equal 1. So this equation here. And we have solved this problem with, you see, P equal 1, Q equal 0. And we are working on an interval of the form 0L. And this is the differential equation, the eigenfunction equation, and the boundary conditions are particular cases of this boundary condition that we called Dirichlet, Neumann, or mixed. For example, Dirichlet boundary conditions are conditions where these two coefficients are 0, and then we are looking for solutions that these coefficients now are 1, and we are looking for solutions where the functions at the end of the interval takes value 0. That would be Dirichlet. And we also have Neumann and mixed. We have solved, there are two types of mixed boundary conditions, and these two, so there are 4 types of boundary conditions where we have solved this problem. The solutions of Sturm-Liouville problems, this type of problems, have very nice properties. Among these properties we highlight 2 properties. So first of all, these problems have infinity many solutions that we label with lambda n and yn. There are several ways to label the eigenfunction. We can start with n equals 0, 1, 2, 3, and this is what we do for the Neumann problem. But for Dirichlet and mixed problems, we choose to label starting at 1, 1, 2, 3 for these 2 problems. So not always we are going to start at 0, depending which type of eigenfunctions are we talking about. But all these problems, all these 4 problems, there are 4 here because 2 mixed, and in general all solutions to regular Sturm-Liouville problem have the following property. Many properties, but we focus on 2. One is orthogonality, that if we have 2 different eigenvalues, then the corresponding eigenfunctions are perpendicular functions with the appropriate inner product that we have introduced in a previous video. And the next property is the properties of orthogonal expansions. Piecewise continuous functions, let's say f of x on the interval AB, can be written as an infinite expansion in terms of the eigenfunctions yn. This is the property we want to focus today. So here is the orthogonal expansion property in more detail. The eigenfunctions yn, which are solutions of a regular Sturm-Liouville problem, satisfies the following expansion property. And now we are going to write the expansion property in all detail. And we are going to do it in a theorem. That is not right. There it is. Theorem. Suppose we have functions yn for some index n that we are labeling from 0, but this is not important. We can start at 1, 2, 3. It's just, let's fix one possibility. We label with index n from 0, 1 to infinity. These are eigenfunctions of a regular Sturm-Liouville problem on some interval ab. This is the general case. Then, for any piecewise continuous function f of x in that interval, the following equation holds. And here we have an equation that contains on one side the function f, on the other side the eigenfunctions yn. And what we say here is that this strange combination of f plus and f minus of f, that looks like an average, is equal to this sum of some coefficients that we don't know what these coefficients are with the eigenfunctions. So let's start saying what are these coefficients Cn. Well, these coefficients Cn can be computed with the eigenfunctions and the original functions. So you do the dot product of the function with the eigenfunction, and then you divide by the square of the magnitude of the eigenfunction. Recall the magnitude of an eigenfunction is the square root of yn dot yn. So what we have here is the square of this magnitude. And what is this f plus minus that we have here? Well, they are nothing more than the side limits. So grab any point x, and then you take the side limit from the right or from the left. So this is the plus or this is the minus. Here is x0. The side limit from the left or from the right of the function f. Do the average of these two side limits, and this is what goes there. So the theorem continues, but let's explain a little bit why we have this expression here. So, and to do that, let's go to the remark. The theorem, again, there is one more part for the theorem, but it's important we understand first what are we doing here. So this expression that we wrote in the theorem, the average of the two side limits, this is the average of the side limits of a function f at x. In a picture, is something like this. Suppose we have a function that just at the point x0 is discontinuous. It has a jump, like that. The value of the function is this point. Let's zoom up a little bit. The value of the function I define here in this graph at x0 takes this value, but then it has a jump, and then the function continues. The side limit from the right is this number. You see, we are approaching here, so this number. The side limit from the left is the actual value of the function, this number here. These are f plus and f minus, and this quantity here is going to be this value in between, the average of these two values. Okay. This is what happens when the function f has a discontinuity at the point x0. Oops, at the point x0 here. What happens when the function f is continuous, doesn't have a discontinuity? Well, the side limit from the right and the left, they are going to be exactly the same, equal the value of the function. So what we have there is that when the function f is continuous at the point, this whole expression is nothing more than f of x. So what we are saying here in this expression is that this expansion of function is actually equal f of x if f is continuous, and otherwise is the average of the side limit, average. In the case the function is discontinuous. So when the function f is continuous, this whole thing is equal f of x at x continuous. Otherwise, average of the side limits. Okay, this is what the theorem is saying, that we can always write the values when the function is continuous. We can expand the function in terms of eigenfunctions, and when in the points where it's not continuous, what this expression is going to give us the average of the side limits when we choose these coefficients to put there. The other part of the theorem says that if the eigenfunctions you are working with are unit eigenfunctions, then, well, what we have here is going to be 1. So then let's call them these eigenfunctions u of n, unit. Then we still have exactly the same expansion here, but now the coefficient, the formula, doesn't have the denominator because the denominator is 1. That's all. It's a little remark only. This type of expansions, so this expansion here, are generalizations of other type of expansions. So we have seen this type of expansions before, although not with orthogonal functions. Recall that when we have a continuous functions f of x, we can always compute an expansion in terms of power functions, and these coefficients are nothing more than the derivative n of the function evaluated at 0 over n factorial. So there are many types of expansions of functions in terms of other functions, in this case polynomials. Taylor expansion is the most common expansion, and now we are introducing other expansions where instead of polynomials we have solutions of Sturm-Liouville problems, and these eigenfunctions have nice properties because, recall, they are mutually perpendicular, property that we do not have for power functions. X to the power n do not have this property in general. And the only thing we can do here is, well, let's prove that if this expansion is true, well, then these are the coefficients that goes here. And this is what we do next. Let's prove only the coefficient formula. The other part of the theorem, that this expansion can be written so that any function f of x can be written in this form, is more complicated, so we don't do it. But the formula for the coefficient is simple. Suppose we have a function f of x that is written in that way, as a linear combination from n equals 0, let's say, to infinity, of coefficients. Let's use m here. We'll see that in a minute why. Cm ym of x. These are our eigenfunctions. So suppose we have this expression. So now let's compute the dot product on both sides with yn. Let's compute this dot product. So what we are going to get? Maybe over here we are going to get yn dot f is going to be the integral. On one side, this dot product, recall, is the integral from a to b of yn of x f of x dx, but is also equal to, we have here the sum from m equals 0 to infinity of this coefficient cm ym of x, and all that we need to multiply by yn of x, and then we need to integrate that from a to b dx. This is what we did. F is given by this expression, so I put it here. Alright, but now I can do the multiplication term by term, so this sum can go outside. So let's put it outside. This is the sum from m equals 0 to infinity. These are constants, so the constant can be written outside. And then we have the integral from a to b of the function yn of x times the function ym of x dx. But this is nothing more than the dot product. So this is what we are doing after all. M equals 0, infinity of Cm yn dot ym. But recall that ym is perpendicular to yn whenever n is different from m. So this dot product is gonna be 0 when n and m are different. So from all these terms, only one single term survives, and this is one term survives, and this is gonna be the term with m equal n, and here we are gonna have n dot n. And recall this is never 0, so in particular this is actually strictly positive. And well, this is what we have used here, that this is equal 0 if n is different from m, because of this property here. Let's put it in red because it's important. So the conclusion is we have a formula for Cn, and the formula for Cn is Cn is nothing more than yn dot f divided by yn dot itself. Which is the formula in the theorem, is this formula here. Now this formula obviously happens when the eigenfunctions are units, so let's write it here. If, let's put it here, if the function yn is actually unit, so let's say u of n is unit, is a unit eigenfunction, then what we are going to have is that, well, yn dot yn is the same as un dot un, which is 1, and then so we get that the formula for the coefficient Cn in this case is going to be f dot un. The order here really doesn't matter, you can, because the properties of the dot product is given by that, and that's it. So this proves the formula for the coefficients is the result of the fact that the functions, the eigenfunctions, are all mutually perpendicular. Let's see how this calculation looks like in an example. Suppose we have this function f of x that is 0 between 0 and 3, and also between 6 and 9, and then between 3 and 6 is constant and takes value 7, so the function obviously is discontinuous at 3 and at 6. So this function here. So compute the eigenfunction expansion of this function in terms of eigenfunction of this problem, which is is the problem with Dirichlet boundary conditions. Alright, so first of all we know what are the eigenfunctions for this problem. The eigenfunctions for this problem with Dirichlet boundary conditions are proportional to sine functions of n pi x over the length of the interval, but the interval here is, let's write it down somewhere, the interval here L is actually 9. Okay, so the only thing we need to choose is what coefficient we're going to choose for the eigenfunctions to work with. Well, there are two possibilities. Well, there are infinity many possibilities, but the two more simple possibilities are Cn. We choose them all equal 1, and then we have some eigenfunctions yn of x, which are going to be just the sine functions of n pi x over 9. And although the coefficients are all 1, the functions are not unit functions, not unit. And if we want unit functions, then we need to choose the coefficients Cn to be 2 over the length of the interval, which in this case is 9, square root. If we choose this Cn for all the eigenfunctions, then we are going to end up with eigenfunction of this form, proportional to the other eigenfunctions, of course, but with the proportionality factor 2 over 9 square root times the sine of n pi x over 9, and these are actually unit eigenfunctions, because this function satisfies that un dot itself, dot product, is actually equal 1. And obviously they are proportional to each other, so let's say, and clearly, un is just 2 over 9 square root yn. So whatever we do with yn, well, then there are similar results for yn, u and y. So we need to choose one. So actually we are going to do the expansion with both eigenfunctions. We are going to compute the expansion with both. Let's start with yn. So let's use yn of x because it has a factor less. So we have that. Okay, so let's recall that we are computing the expansion for values different from x equal 3 and different from x equal 6, because so we are computing the expansion for all values of x, but at x equal 3 and x equal 6 we are not going to get the value of the function, because the value of the function here at 3 and at 6 is, as you see here, is 7, and our expansion is not going to give us 7 there. It's going to give us the average of these 2 points, so 7.5 on both. So this is that little remark is that at these 2 points where the function is discontinuous, we are going to have 7.5. That is what this expansion is going to give us. And what we need to compute now is what happens for all the other points where the function is continuous, and not 3 and not 6. Since the function is continuous for all these values, then what we are going to have is that f of x, here, f of x is actually equal the sum from n equal, and here we are labeling our eigenfunctions starting at 1. Recall here, so we are not starting at 0, but we are starting at 1 to infinity, and then we are going to have coefficients Cn, and we are using the functions yn, because that's the function we chose. And recall this expression is for x different from 3 and x different from 6. All right. What is the coefficient Cn given by? Is given by the dot product of f with yn divided by how long is yn, the magnitude of yn squared. All right, so we need to do this calculation. Let's start with the denominator. We start with the denominator because we already know what the denominator is. We have done in the previous videos that yn for this Dirichlet problem is just this integral, the integral of sine square n pi x over L, and here L, and this is going to be equal L over 2, and here L is 9, and by the way, this is the calculation used to find out that these functions are unit. You see, you have that factor here, 1 over that factor, square root, and that factor appears there because of that. But we know all that. So the only thing we need to compute is the numerator. So let's do it. F dot yn. Well, this is nothing more than the integral from 0 to 9 of f of x multiplied by the sine, what happened here? By the sine of n pi x over 9 dx. But now we use the definition of f. Notice the definition of f is 0 between 0 and 3, and also 0 between 6 and 9. You have here that. So the only part of the integral that is different from 0 is between 3 and 6. That's the only part of the integral that survives, and in that interval the function takes value 7. So because of that, this is the same as the integral from 3 to 6, nothing else, and here the function is the function 7 times sine of n pi x over 9 dx. So it's a very simple integral now because the 7 can be written outside. The integral of the sine, well, is negative cosine, so it's negative 1. Well, we have a factor there, and then a cosine of n pi x over 9. What is the factor? The factor is this coefficient upside down, so 9 over n pi. And why is that? Because when you compute the derivative is going to be minus sine, and then multiply by n pi over 9, but this is going to cancel that, so we are going to get exactly that. Perfect. It works. And now we need to evaluate that in 3 and 6. All right. So we can rewrite this as negative 63 divided by n pi, and then we need to evaluate the cosine of n pi over 9 at 6 minus the cosine of n pi over 9 at 3. So what I'm going to do, because of this negative sign, I'm going to flip the order of the terms, and then I'm going to simplify, and we get our final result, 63 over n pi. Then we are going to have the cosine of n pi over 3 minus the cosine of 2n pi over 3. There's nothing much we can do, so this is how this inner product looks like. And what do we do now? Well, we recall that, so let's put it here, recall that yn dot yn in this case is 9 over 2. Then what we can do is compute Cn now. Cn is going to be 2 over 9, 63, but recall 63 was 7 times 9, that was 63, divided by n pi, and then we have here the cosine of the n pi over 3 minus the cosine of twice n pi over 3. Okay, so we can do a little cancellation here, and then we obtain 14. That's it for. So, well, let's write it down here. Cn is going to be, well, let's do it. 14 is only one little step, but let's find the final expression for the coefficient. Okay, this is our coefficient Cn. And then we have our expansion. Recall, this is the expansion of the function f of x, which is going to be now a sum starting with 1 to infinity. This is how we label our eigenfunctions. We have here 14 n pi. Here we have the cosine of n pi over 3 minus the cosine of twice n pi over 3, and all that is multiplied by a sine of n pi x over 9. And let me write here that ground color, that this here is what we call the coefficient Cn, obviously, and this is our eigenfunction that we chose to be yn of x, and that is the expansion. So we could end up here. So this is the calculation of the expansion when we use the eigenfunctions yn to be sine of n pi x over 9. But what happens if we choose the other eigenfunctions? Well, there is a little detail that we need to be careful, so I'm going to do the whole calculation just to emphasize that detail. If we choose unit, suppose we choose the unit eigenfunctions. So let me write down something before we move on to the unit eigenfunctions, and this formula is for x different from 3 and x different from 6. Okay, just to be clear, because there. Just to be clear what we are doing. And if we choose unit eigenfunctions, so now the unit eigenfunctions are un is equal 2 over 9 square root sine of n pi x over 9. So one would say, oh, the only thing that is changed is a factor here, 2 9 square root or something like that, and that would be wrong. So it's a little bit more tricky than that. So if we choose those functions, let me write the expansion f of x as a sum from n equal 1 to infinity of some other coefficient Cn, and then the eigenfunctions un. And of course this is for x different of 3 and x different from 6, because the points where the function is discontinuous we have some other formula. Okay, so what is d in this case? With dn just f dot un. Okay, but recall that un is just 2 over 9 yn. Okay, these two things say that the coefficient dn that we need to put in the expansion is 2 square root of 9, 2 divided by 9 square root, sorry, all that coefficient, then f dot yn. Okay, but we already have f dot yn, so is not this coefficient because it has the 14. Is this one? That is the one with the 63. Okay. So then the coefficient dn, we don't need to do the integral again, is going to be 2 over 9 square root. Then we are going to have the 63 over n pi, and then the two cosines. The cosine of n pi over 3 minus the cosine of 2 n pi over 3. Okay. So that is the coefficient dn that goes in the expansion. So now we write down the whole expansion, and then we are going to have that f of x can be written as a sum from n equal 1 to infinity. Now we are going to have the 2 over 9 square root. Then we are going to have the 63 over n pi. Then we are going to have the cosine of n pi over 3 minus the cosine of 2 n pi over 3. And then we are going to have the unit eigenfunctions. So recall that we need to, this is the coefficient d, and now we need the un that has again that coefficient one more time. So 2 over 9 square root sine of n pi x over 9. So this is it's a little bit more complicated than one could think. So here is what we call the un. And now this is the coefficient dn. Now let's bring back the formula we had before that we computed with the non-unit eigenfunctions. Copy. And let's compare. What is going on here? So what is going on is that the coefficient Cn, this coefficient, is constructed with this coefficient and the square root coming from the d and the square root coming from the unit eigenfunctions, because this here is the yn. So everything else has to be c. Okay, and it is the case because 2 over 9 square root 63 and 2 over 9 square root, this is obviously 2 over 9, and then recall the 63 was 6 times 9, so we cancel, and this is the 14 that we have here. Alright, so that's the a little remark I wanted to do, that if you don't choose unit eigenfunctions, or it could be a little bit tricky to relate calculation with non-unit to unit eigenfunctions, because this factor splits into part into the coefficient, part into the eigenfunction. The factor 2 over 9 split into two parts. One square root goes here, one square root goes there. Anyway, how does it look like this eigenfunction expansion? I have two pictures here. So in the picture we see we have the function f. It takes value, this is not the right function, okay, so this is from 0. Yeah, I screwed up the function, because what function do I have here? I have up to 9, but it takes value 6. In the graph I for some reason I put value 9. Okay, but suppose that we have, it's the same thing, but I have a different value here. It's a little bit higher, the value, you see. This graph should have been, I don't know, here. Anyway, pretty much the same. This is the case n equal 3 when you have only n equal 1, 2, and 3. So you are going to have this approximation of the function. It's a pretty bad approximation. But as long as you put more terms, for example, here we have 50 terms, look what is happening. The expansion is looking very closely now to the function, but with oscillations. So this is what you are doing. You are approximating a function that has no oscillations with oscillatory functions, and what happens is there is a lot of oscillation super fast and with very small amplitude here, here, and here, and then a big jump, and the jump is such that the value of the function at the discontinuity is exactly the average of the two values of the function, the two side limits. So this is how these expansions look like in this example. We have one more example, but since we are running out of time, I'm gonna show you the calculation instead of writing everything. I'm gonna unveil the calculation and then you can do it yourself and compare with this video. So, example, suppose that we have this function now, and it's a little bit more complicated than before because we have the function x. X in the first half of the interval, constant on the second half. So, in the first half and then constant. Now this is a continuous function, so the eigenfunction expansion is going to give you exactly this function. There is no average of side limits here because all the average of side limits are equal to the value of the function. The function is continuous. So we need to find the eigenfunction expansion of this function in terms of eigenfunctions, solution of this problem, that our usual differential equation, and looks like, oh, here, derivative. So this is a mixed eigenfunction problem. So how do we solve this problem? I'm going to show you the calculations, and then you can do it yourself on your paper later. After the video, you stop the video, and you can compare your calculation with this, what we show here. So what are the eigenfunctions of this problem? Well, we have solved that in a previous video. They are sine of 2n minus 1 pi x over 2l. Recall here L is 10, and this eigenfunction for the mixed problem having the denominator 2l. So 20. These eigenfunctions are not unit, like we did in the previous example. Let's work with that eigenfunctions first, and then we do the calculation with the unit eigenfunction to compare. Okay, so what we need to do is we need to find the expansion of this function in terms of these eigenfunctions now. They have the 2n minus 1, they have the 20 here instead of the L, and the coefficients are going to be given by the same formula as before. So we need to do this calculation, but the denominator is easier. We start there. Recall that the eigenfunction dot itself is always the length of the interval divided by 2. Our length is 10, so this dot product has to be 5. And the way we prove this formula, recall, is using this trigonometric identity that changes a sine square into a cosine of twice the argument. And the reason of this 1/2 is because of this 1/2 there. Alright, so the denominator is done, is 5. So the only thing we need to do is compute the numerator, and I'm going to show you here what is the calculation pretty fast. It's going to be the integral from 0 to 10 of the function and then the eigenfunction. But this function has two different definitions according whether we are in 0,5 or we are in 510. So we need to split the integral in 5, because on one side of the integral between 0 and 5 the function is x, and on the other side of the interval the function is 5. So this is what we do here. We split the integral between 0 and 5, where the function is f is x, and then the integral between 5 and 10, where the function is this 5 here, which I already took it out of the integral. So we need to do these two integrals. The integral on the right is simple, it's like the integral in the previous problem. This one is a little bit more complicated. So we need to go to the table, and in the table we have this integral, x times a sine of some coefficient is whatever this coefficient is in the denominator, and then 1 over that square sine, and here is cosine with the negative sign and with the x. So this term is complicated, this is simpler. So let's do it. Here, if you do it carefully, you're gonna get that these two terms are these two terms here. You see, because they are evaluated in 0 and 5. In 0 and 5. So we have the negative, we have the x. The a is this coefficient, that's a. So we need 1 over a, is right here, then a cosine of that, and then 1 over a square, there it is, times the sine, evaluated on 0 and 5. And then we have here the 5, we still have the 5, and then we need to integrate the sine, which is going to be negative cosine, and here we flip it. But this is between 5 and 10. Alright. Then we evaluate at 5, we evaluate at 10. You have to be careful at 5. This is you're gonna have a 5. It's gonna cancel and you get a 4. Then this one also is gonna be a 5. Cancel, you get a 4. There it is. These are the two terms evaluated at 5. What happens when we evaluate at 0? Well, this is gonna be a 0, so 0, and the sine is gonna be 0, so 0. So these are the origin of the two zeros, is that evaluation. Here we have evaluation at 10 and 5. So this is at 10, you put 10, you get 2, and then you put 5, you get the 4. But in this particular problem, this term is going to be exactly that term with the opposite sign, so they cancel out. And what happens here? Well, recall that cosine of odd multiples of pi over 2 is always 0. So this goes away, this cancels out, and we get only one term. And that's the result. And now this is the dot product, this is the other dot product, we put them together and we get this expansion for the function f. This is the function and this is the coefficient. So they are here for you to compare when you do the calculation yourself. Now what happens if we use the functions, the unit functions, that they have this coefficient here? Recall L is 10 in this problem. Well, then we are going to get this extra factor, and then when we do so one eigenfunction is proportional to the other with this new factor now. So now we have an expansion of the function f with new coefficients. This the eigenfunction is going to introduce a 1 over square root of 5 here, and this function dn is only given by this formula, and this is exactly what we did before. And recall, when we replace un, well, we create one more factor, 1 over square root of 5, and this calculation is already done. This we already did. It's a long calculation, and this is the formula we got right here. So we put everything together, and the only difference is that we have this extra factor 1 over square root of 5 in the coefficient, but we also have it in the eigenfunction. So this is the expansion using unit eigenfunctions. Here is the unit eigenfunction, and here is the coefficient d. The coefficient d has this factor, the unit eigenfunction has this factor. When they put them together, is 1 over 5, and 1 over 5 divided, that is divided in 400, is going to be the 80 we found before. So here you have another solved example to help you practice how to compute the coefficient Cn in these expansions, orthogonal expansions. We finish this video with a brief comment, and the comment is about the relation between this eigenfunction expansion and the Fourier expansions. And we notice that we want to remark that the orthogonal expansion above are particular cases of what is called Fourier expansions. So we were working with Fourier expansions already, but the general Fourier expansion comes from a different problem that is called periodic Sturm-Liouville problems. A periodic Sturm-Liouville problem on an interval, and looks, the interval here is symmetric around 0, negative L, is to find eigenvalues lambda and non-zero functions, so eigenfunctions, solution of the same differential equation, but with what they are called periodic boundary conditions, which are this, which says that the function on one side of the interval is exactly the same as the function on the other side, and the same happens to the derivative. So what we are saying here is we have in this type of periodic Sturm-Liouville problems, we have an interval that is symmetric around 0, and the values of the function that we are looking for on these two sides have the same values. So this is the same as if we bend this interval and we join the two sides, and instead of an interval we are working on a circle. So essentially this periodic Sturm-Liouville problem is nothing more than a Sturm-Liouville problem on a circle. And we convert this into a circle because we are saying the values of the function here and here are the same, so we are identifying these 2 points and then we are working on the circle. So this is just to help understand why people are interested in these boundary conditions, and this condition makes sense when instead of working on a straight interval you are working on a circle. Alright, so this is a periodic Sturm-Liouville problem, and that periodic Sturm-Liouville problem has solutions, and one can calculate the solutions, and we are going to have that we have the eigenvalue 0 with the eigenfunction constant, and then eigenfunction of the same form as before, n pi over L squared, but the eigenfunctions corresponding to the eigenvalues are both cosine and sine, not just one or the other like in the previous problems. We have both. That's why what we have done is a particular case of this type of eigenfunctions. And then there is a theorem that says, oh well, if you have these eigenfunctions, then you can make an orthogonal expansion of piecewise continuous functions with piecewise continuous derivative, doesn't matter, in that interval. And again, we are going to have the same thing here. The average of the side limit is going to be equal now an expansion that contains both sine and cosines. In our expansion we have only sine or cosine depending which eigenfunction we are using. In general you can have both. And the formula for the coefficient is the same as before. It's the dot product of a function with the eigenfunction divided by the magnitude square of the eigenfunction. But now we have more, so we have 3 coefficients, 3 formulas for the coefficients. So this is the general Fourier series expansions. We are not going to focus on these expansions, only on the particular cases we studied before, because the particular cases is exactly what we need to solve the heat equation. So this is a good place to stop. See you guys in the next video.